Hi everyone, myself Dr. Ashok Babu, working as Professor and Head EC Department. So in this video, I am going to discuss about some problems in magnetostatics. The problem first one is, so a ring of radius 5 centimeters is placed on a plane z equal to 1 centimeter, so that its center is at 0, 0, 1 centimeter. So if the ring carries 50 milliamps current along A5, then we need to find out the magnetic field intensity. So here magnetic field intensity, we need to find out magnetic field intensity at 0, 0, minus 1 centimeters, 0, 0, 10 centimeters. So this is the problem given. So here the solution is, we need to find out the solution as. So here we know that the magnetic field for a ring is, so it is given as a ring. We know that the magnetic field for a ring is H is equal to, so it is IA square into AZ by 2 into A square plus H square whole power 3 by 2. This is a magnetic field for a ring. Okay, so here we need to find out the magnetic field intensity at point 0, 0, minus 1 centimeters. So here to find out that, we need to find out the Z value. So here already is given as Z is equal to 1. So which is placed at 0, 0, 1. So let us assume Z is like this. Z is like this 1. And here we need to find out the this point is at 0, 0, 1. 1 is at Z equal to 1 is at 0, 0, 1. Now we need to find out the Z value at 0, 0, minus 1. So it is 0, 0, minus 1 is, it is 0, 0, minus 1. So first we need to find out the Z value. So Z values, we can find out the Z value as Z is equal to 1 minus of minus 1. 1 minus of minus 1. Therefore it becomes Z equal to 2. So the Z value is 2 centimeters. Therefore the magnetic field intensity is H is equal to, so I is given as I is equal to 50 milliamps. Substitute the I equal to 50 milliamps. Then A is, radius A is given as 5 centimeters. Therefore A square is, convert the centimeters into meters. Therefore it is 25 into 10 power minus 4 meters by 2 into A value. Again A is the radius, it is 5 square plus, again H is the height of the, height is given as, height is nothing but this value, Z is nothing but the height value. Therefore it is 2 square whole power 3 by 2. So here we need to convert the same into centimeters into meters. So if you convert the centimeters into meters, minus 10 power, here we have 10 power minus 4 whole power 3 by 2. Therefore 10 power minus 4 into 3 by 2, 2 2s. Therefore it becomes 10 power minus 6. Therefore it is 10 power minus 6. So if we simplify the same, we have 400.2 into AZ milliamps per meter. Now we need to find out the second value. So the second point is placed at 0, 0, 10 centimeters. So it is along the right hand side. It is 0, 0, 10 centimeters. So now we need to find out the again height value, Z value. So Z value is 10 minus 1. So therefore here the Z value is Z equal to 10 minus 1. Therefore it is 9 centimeters. Again we need to substitute the same values. Therefore the current I is given as 50 milliamps. Therefore 50 into 10 power minus 3 into 25 into 10 power minus 4 by 2 into 5 square plus 9 square. Here height is the 9 square whole power 3 by 10 power minus 6. Therefore the value is 57.3 milliamps per meter. So this is in this way you can find out the electric field intensity along the Z axis. Next one. Next problem. So a solenoid of length L and radius A consists of N turns of wire carrying a current of I. Show that at point P along its axis, we need to find out the H is equal to Ni by 2 into cos theta 2 minus cos theta 1 into AZ. We need to prove that the magnetic field intensity of a solenoid is Ni by 2 into cos theta 2 minus cos theta 1 into AZ. So where N is given as N is equal to Ni by L, where N is the number of turns in a solenoid. Theta 1, theta 2 are the angles subtended at point P. Theta 1 and theta 2 are the angles subtended at point P by the end turns, both the end turns. So theta 1 is the angle made by the end turn of the starting stage. Theta 2 is the angle made by the end turn of the end stage. So here again we need to prove that if L is very greater than A, if L is very greater than A, at the center of the solenoid, we need to prove that H is equal to N into I into Az. So here where A is the radius of a solenoid, L is the length of the solenoid. And at this point P, so let us assume some theta is there. So here due to some current element, so here some theta is there. So let us assume this length is Z and this length is A. So we need to prove that H equal to Ni by 2 into cos theta 2 minus cos theta 1 into Az. So here from this, let us assume this triangle. So from this triangle, we can write tan theta. So tan theta is equal to A by Z. Tan theta equal to A by Z. Or Z is equal to, we can write, or Z tan theta equal to A. Z tan theta equal to A, or Z is equal to, we can write here, Z is equal to A by cot theta, or Z is equal to A into, A is equal to tan theta, A by tan theta, or Z equal to A cot theta. Z equal to A cot theta. Since the solenoid consists of circular loops, the magnetic field H at point P by an element of solenoid of length dz is given by, so it is dHz is a differential magnetic field. So the differential magnetic field dHz equal to, it is ideal dot A square by 2 into A square plus H square whole power 3 by 2, because the solenoid is having the circles like this. It is having the circles like this. So it is having the circular loops. So directly we can write the magnetic field intensity formula dHz equal to ideal A square by 2 into A square plus H square whole power 3 by 2. So here in place of dl, here I am writing n into dz because it is placed along the z axis. So here in place of dl, here I am writing n into dz. But n is nothing but, small n is nothing but capital N by L. So capital N by L into dz. So from figure we can write tan theta is equal to A by Z. Therefore here we can write the dz is equal to, A cot theta. Differentiate the equation on both sides. Sorry, Z is equal to A cot theta. Differentiate the equation on both sides. Therefore dz equal to A into cot theta. Differentiation of cot theta is minus cosecant square theta. D theta. Minus cosecant square theta d theta. So here again from the from figure, here we can write cos theta equal to Z by root of A square plus cos theta equal to this Z by root of A square plus H square, and sin theta equal to, we can write the A by root of A square plus H square. We can write A by sin theta equal to A by root of A square plus H square. So here we can readjust the equation as, the same equation as, so here my dz equal to minus A into cosecant square theta d theta. So here cos theta is equal to, so here we can write sin theta equal to, we can write A by root of A square plus H square. Sin square theta equal to or cosecant theta equal to, here we can write root of A square plus H square by A. Therefore cosecant square theta equal to, we can write A square plus H square by A square equal to cosecant square theta. Therefore directly, so here I am substituting cosecant square theta equal to root of minus Ez, again minus Ez, minus A into root of Z square plus, so here I am writing minus A into root of Z square plus A square whole power 3 by 2 by A square. But here again we know that from the formula tan theta equal to A by Z. Therefore we can write A equal to Z tan theta. Therefore here I am writing minus Z tan theta into Z square plus A square whole power 3 by 2 by A square. But tan theta can be expressed as sin theta by cos theta. Therefore minus Z into sin theta by cos theta into Z square plus A square whole power 3 by 2 by A square. And we can express the cos theta value and sin theta value. So here we can express the cos theta as, cos theta is equal to, we can write it as Z by root of A square plus H square. Z by root of A square plus H square. Therefore it is minus Z into sin theta by, so here cos theta equal to, we can write z by root of a square plus root of a square plus z square into z square plus a square, z square plus a square whole square. Actually, it is whole square, z square plus a square whole square by a square is there. So here I am cancelling the z term, and here it becomes minus sin theta into a square plus z square whole power 3 by 2 by a square into d theta is there. So this is the expression. So this expression can be written as, in place of dz, here we can write minus sin theta into d theta into z square plus a square whole power 3 by 2 by a square. So same if you substitute in the equation, and if you integrate the equation, it is dhz equal to, here we can substitute dhz equal to, so here already we have I square into a square into n dz by 2 into a square plus a square whole power 3 by 2. So here if you substitute the dz value, so dz value, if you substitute dz value, it is I into a square into n into, so dz is minus sin theta into a square plus z square whole power 3 by 2 by a square into d theta by, we have already 2 into a square plus h square whole power 3 by 2 is there. So these two cancel each other, and a square cancel each other. Then we have, finally we have minus ni by 2 is there, minus ni by 2 into sin theta into d theta, minus ni by 2 into sin theta into d theta. So if we integrate the equation on both sides, hz equal to minus ni by 2 integral sin theta into d theta between the limits theta 1 to theta 2. So integral of sin theta is minus cos theta. Therefore hz equal to, we can write ni by 2 into cos theta between the limits theta 2 to theta 1. So h is equal to, you can write ni by 2 into cos theta between the limits theta 2 to theta 1. Therefore you can write here ni by 2 into cos theta 2 minus cos theta 1. Hence the given one is proved. So here again we can substitute the n equal to small n equal to capital N by L. So if you substitute small n equal to capital N by L, the equation becomes capital N into I by L into 2 between with cos theta 2 minus cos theta 1. So here again we need to prove the other one. At the center of the solenoid, means just go back to solenoid. So at the center of the solenoid, so it is the center of the solenoid. So here we need to assume that the distance of the solenoid is L by 2. So the distance is L by 2 and the radius is A only. So here if you find the same one, let us assume it is L by 2, it is A. So the magnitude is L by 2 square plus A square. L by 2 square plus A square. So here the hypotenuse is. So from this, therefore cos theta 2, if you find the cos theta 2, so from this cos theta 2, let us assume this some theta 2 or this one or this one. So if you find the cos theta 2 equal to L by 2 by root of L by 2 by root of L by 2 whole square plus A square. Root of L by 2 whole square plus A square. L by 2 by root of A square plus L square by 4 whole power 1 by 2. Which is equal to minus cos theta 1, because which is exactly at the center. So theta 1 is in negative quadrant and theta 2 is in positive quadrant. Therefore cos theta 2 equal to exactly minus cos theta 1. So here if you substitute these two angles in this equation, so here cos theta 2 equal to, we can substitute L by 2 into root of A square plus L square by 4 minus, so again here we can substitute this value. So minus of minus will become the positive. So then we need to add the two expressions. So if you add the two expressions, L by 2 plus L by 2 by root of A square plus L square by 4. That is L by 2 plus L by 2 is, it is 2L by root of A square plus L square by 4. So 2L, here we can cancel the 2. So therefore you can cancel the 2. Then we have I into NL. So here we have N into I is there. We have L is there. Therefore 2L by 2. 2 to cancel. We have L is there. So L by 2 into root of A square plus L square by 4 into AZ is here. So now if L is very greater than A, if L is very greater than A means, so L is the length of the solenoid is very greater than the radius. So if the length is very greater than radius, so the two angles, the two tan, here it is tan theta 1, theta 2. So theta 1 will move towards the 0 axis and theta 2 will move towards the 182 degrees. So both the will goes opposite directions. Theta 1, theta 2 will goes opposite directions. Then theta 2 equal to 0 degrees, theta 1 equal to 180 degrees. So if you substitute in the same expression, so h equal to ni by 2 into cos theta 2. Cos theta 2 is 0. Therefore cos 0 is 1 minus cos 180 is minus 1. Therefore it is h is equal to, we have ni by 2 into 2. 1 minus of minus 1, 2. So it is 2 into 2. H is equal to ni. We have h equal to ni into Az. Or if you substitute n equal to ni by L, we have ni in by L Az. So this way we can find out the derivation for solenoid of the magnetic intensity of a solenoid. So the magnetic intensity of a solenoid is H is equal to, here we have the formula, ni by 2 into cos theta 2 minus cos theta 1 into Az. Next, this is the other problem. So a toroid whose dimensions are shown in figure has n turns and carries a current I. Then we need to determine the magnetic field intensity inside and outside the toroid. So here toroid is also having the same circular loops. So here we need to apply the Ampere circuit law to find out the magnetic field intensity of a toroid. So here here the dotted line is, let us assume there is some uniform current distribution is there. So when uniform current distribution is there, then only we can apply the Ampere circuit law. Therefore assume uniform current distribution throughout the circle. So when there is some uniform distribution, then construct a mathematical circle, so which is known as Amperian circle. Mathematical circle or Amperian circle. So then we can apply the Ampere circuit law to Amperian path. So where A is the radius of Amperian path, rho is the radius of Amperian path, and rho A is the actual radius where rho A is the actual radius of the inner conductor or inner part of the toroid. Rho A is the radius of inner part of the toroid, and rho is the radius of Amperian path or mathematical circle. Therefore, here if you apply Ampere circuit law, according to Ampere circuit law, the line integral of h into dl equal to I enclosed. Therefore, here if you find out the same, or if you find out the integration, so here h is a constant, keep outside. It is into 1 into dl. 1 into dl is equal to I enclosed. So because of it is a circle, we need to assume the circumference of a circle. So here the circumference of a circle is 2 pi rho. Therefore, h into 2 pi rho is equal to I enclosed. H into 2 pi rho is equal to I enclosed, where I enclosed is equal to nothing but number of turns is given as n. Therefore, the current enclosed is n into I. Therefore, the magnetic field intensity H is equal to, it is n into I by 2 pi rho. N into I by 2 pi rho. So here the condition is rho is between the rho naught minus A plus rho naught plus A. Rho naught plus A. So here we can where rho naught is the mean radius of the toroid as shown in figure. So and as an approximation value of H, we can write the approximate value of H is, it is n in place of here n here we can write the magnetic field intensity is Ni by 2 pi into rho naught. Ni by 2 pi into rho naught. So which is equal to, that is Ni by L, where L is the total circumference of a circle here. This is the inside the magnetic field intensity inside a toroid. So outside the toroid means we need to add the two currents. So inside the current already we have Ni is there. So outside the toroid means we have minus Ni. Therefore, the total magnetic field intensity outside the toroid is equal to 0. current is 0. When current equal to 0, automatically the magnetic field H is equal to 0. According to the Ampere circuit law, the line integral of H into dl is equal to I enclosed. So if I enclosed equal to 0, automatically the magnetic field intensity H is equal to 0. So this way you can find out the magnetic field intensity of a toroid inside and outside the toroids. Next one. So given the next problem, given the magnetic vector potential A is equal to minus rho square by 4 AZ Weber per meter, and calculate the total magnetic flux crossing the surface. Phi is equal to pi by 2, and rho dimensions are given, Z dimensions are given. So rho is ranging from 1 to 2 and Z is ranging from 0 to 5. So here we need to find out the magnetic flux density. So here the magnetic flux density, we know that the vector magnetic vector B is equal to, we can define as B is equal to del cross A. B equal to del cross A. So here we can find the del cross A. We need to find out the del cross A. So del cross A equal to, so here in cylindrical coordinate system, we have A rho, A phi, AZ, dou by dou rho, dou by dou phi, dou by dou Z, and here we have given AZ is given, and remaining two are zeros. Therefore 0, 0 minus rho square by 4 is given. So here we need to find out the depth of the matrix. So the depth of the matrix is A rho into, so here these two cancel each other. Then we have 0, 0 minus of rho square by 4, minus A phi into, both are zeros, plus AZ into, next one is AZ into, we have zeros. AZ into, we have 0, 0, 0 only. Therefore we have A rho into, we have the expression A phi into so here we have A phi into minus A phi into, it is 0, dou by dou rho into minus rho square by 4 is there. Therefore here we have A rho into dou by dou phi of rho square by 4, plus we have A phi into dou by dou rho of rho square by 4. So because differentiation of phi for rho is 0, therefore no need to consider this one. Therefore we have A phi into dou by dou rho of rho square by 4. Dou by dou rho of rho square by 4 is, it is 2 rho by 4. 2 rho by 4. Then 2 cancel each other. Therefore we have rho by 2 into A phi. Rho by 2 into A phi. So therefore B is equal to, we have del cross A, which is equal to rho by 2 into A phi. Rho by 2 into A phi. Now let us assume, because in spherical coordinate system, we can assume ds equal to d rho dz A phi. D rho dz A phi. Now if you substitute all these values, then we can find out the flux. We have the formula, flux psi is equal to integral B into ds, which is equal to, so here in place of B, we need to substitute rho by 2 into A phi. So 1 by 2 into integral, the limits are given as z equal to 0 to 5 and rho equal to 1 to 2, rho dz. Because in place of ds, I am substituting d rho dz A phi. So already rho is a rho, therefore rho d rho dz. So we need to integrate this separately. So here if you integrate this one, it is 1 by 2 integral z equal to 0 to 5 into dz, and integral rho equal to 1 to 2 rho d rho. So it is, if you integrate this one, we have 1 by 2 into integral of 1 into dz is 1, between the limit 5 minus 0, therefore we have 5 into, so here the integral of rho is, it is rho square by 2 between the limits 2 to 1. Therefore it is 5 by 2 into 4 by 2 minus 1 by 2. So it is 3 by 2 for 15 by 4. The answer is 15 by 4. So therefore the flux, the total magnetic flux crossing the surface phi is equal to 15 by 4 or it is 3.75 Webers. 3.75 Webers. Next. So calculate the self-inductance per unit length of an infinitely long solenoid. So we need to calculate the self-inductance of a infinitely long solenoid. So here we know that for infinitely long solenoid, the magnetic flux inside the solenoid per unit length is, it is magnetic, B is equal to mu H, where H is nothing but I into N. H is nothing but the I into N, number of, where N is equal to N by L. N is the number of, capital N is the number of turns per unit length. If S is a cross-sectional area of a solenoid, then the total flux through the cross-section is, psi is equal to B into S. The total flux psi is equal to B into S, where B is nothing but mu In. Therefore, mu In into S, where S is a surface cross-sectional area of a solenoid. Since the flux is only for a unit length of a solenoid, then the flux linkage can be calculated as the lambda dash equal to lambda by L, where lambda dash is the flux linkage per unit length. Therefore, lambda dash equal to lambda by L. So, lambda by L, which is nothing but lambda by L is equal to N into psi. Lambda by L is equal to N into psi, where N is the number of turns. Again, N is number of N equal to N by L, where capital N is the number of turns per unit length into psi. The flux linkage is equal to N into psi. Lambda is equal to lambda dash equal to N into psi, which is equal to, the flux linkage is equal to this mu, but psi is nothing but mu I ns. Therefore, mu I ns into N. Therefore, mu N square into Is. And thus, the inductance per unit length is, we need to calculate the inductance per unit length. The inductance per unit length is L dash equal to L by L is the inductance per unit length. So, which is equal to lambda dash by I, which is equal to lambda dash by I, which is equal to, so here lambda dash by I means, so already lambda is equal to, we have mu N square Is. So, lambda dash by I equal to mu N square S is the inductance of a infinitely long solenoid. Inductance of a infinitely long solenoid. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.